Ever been sitting on a train, looking out the window, and for a second you feel like you're stopped and the world is rushing past?
Oh yeah, that weird little perspective shift.
Exactly, that feeling. It's kind of a neat little doorway into what we're diving into today. Einstein's theory of relativity. We're using sources you sent us, listener, including some from Einstein himself.
And our goal really is to unpack these big, sometimes kind of mind-bending ideas, make them click, and show you how they, well, changed everything in physics.
And it's not just us non-experts who find it tricky, right? Even physicists had some trouble wrapping their heads around it initially.
That's true. And it's worth pointing out, while special relativity built on work from others too,
Yeah.
general relativity, that was really Einstein's unique, groundbreaking contribution.
Okay, so let's get into it. Einstein didn't just tweak physics, he sort of rewired our fundamental concepts, space and time.
Right. We usually think about geometry with rulers, measuring distances, but relativity flips that. It suggests space-time geometry is more about uh, chronometry, measuring time.
Clocks, not rulers. Why?
Well, think about it. If you want to measure a distance with a ruler, you need to know where both ends of the ruler are at the same time. And defining at the same time for things in different places, that turns out to be complicated. Clocks are more fundamental.
Okay, so special relativity uses this idea called Minkowski space, like a flat background.
Exactly. It's the stage for physics without gravity. But gravity messes things up. Einstein realized that to account for gravity, that stage, space-time itself, can't be flat. It has to be, well, warped, irregular, curved.
And that curvature is gravity?
In Einstein's view, yes. This dynamic geometry is the gravitational field.
Wow. So what was the spark? How did he connect gravity to this curvature?
The big light bulb moment was realizing that if you're, say, free-falling in a gravitational field like an astronaut in orbit, you don't feel gravity's force. Those free-falling frames are the truly inertial ones.
That's kind of backwards to how I normally think.
It is. And connecting that idea with his other huge insight, that mass and energy are equivalent, EMCEPI, that led him to this revolutionary concept.
Right.
Gravity isn't a force pulling things, it's the curvature of space-time caused by mass and energy.
Mind blown.
Yeah.
Okay, let's back up slightly to special relativity first. It starts with a principle, right?
Yeah, the principle of relativity, but in a restricted sense.
Right.
Basically, if you're in a non-accelerating frame of reference, like that smooth train ride, the laws of physics work the same way as for someone standing still or someone on another train moving smoothly. Only relative motion matters.
Seems reasonable enough until light enters the picture.
Precisely.
Yeah.
Because one fundamental law seems to be that light in a vacuum always travels at the same speed, see, no matter what.
And that seems to clash, doesn't it? If I shine a light forward on that moving train, shouldn't someone outside see it moving faster? Like the speed of light plus the speed of the train.
That's the core puzzle.
Yeah.
Einstein's brilliant solution involved rethinking something we take completely for granted. Simultaneity, things happening at the same time.
Ah, the lightning strike example. I remember reading about that.
Exactly. Imagine lightning hits both ends of the moving train, points A and B. Someone standing on the ground right in the middle sees the flashes arrive together, simultaneous.
Makes sense.
But now think about someone on the train also in the middle, because they're moving towards the light flash from, say, point B and away from the flash from point A.
They won't see them arrive at the same time. The one they're moving towards gets there first.
Right, so simultaneous depends on who's looking. It's relative. And to even define it, you have to assume light travels at the same speed in all directions.
Which means time itself must be relative too. Different observers experience time differently.
That's the profound consequence. The old idea of a universal clock ticking the same for everyone, it just doesn't work if the speed of light is absolute. Each reference frame has its own time.
Okay, so if space and time measurements change between observers, how do we connect them mathematically?
That's the job of the Lorentz transformation. It's a set of equations that tells you how to translate the space and time coordinates from one uniformly moving frame to another.
And this transformation is what keeps the speed of light constant for everyone.
Exactly. It shows how space intervals and time intervals stretch or shrink relative to each other to preserve c. It solves the apparent contradiction.
And this leads to some really weird effects like length contraction.
Yep. An object moving very fast relative to you will actually appear shorter in the direction it's moving. It's not physically squished. It's a consequence of the geometry of space-time.
So space itself isn't rigid.
Not in the way we intuitively think. And this also implies that c, the speed of light, is the ultimate speed limit. Nothing with mass can reach it because reality itself warps to prevent it.
Were there hints of this before Einstein?
There were. Experiments like Fizeau's, looking at light speed in moving water, showed that simple velocity addition didn't work for light. The results actually fit the Lorentz transformation predictions better. And special relativity also tidied up the theories of electricity and magnetism, showing connections nobody had seen before.
Okay, pausing here. What are the absolute must-remember consequences of special relativity?
Number one has to be the unification of mass and energy, EMC Soroco. It's not just an equation. It means mass is a form of energy, incredibly concentrated energy.
And that energy is there even if the object is just sitting still, the MC-SAR part.
Absolutely huge amounts of energy locked up in even tiny amounts of mass. We don't notice the mass change when we, burn wood because the energy released is small compared to the total mass energy. But in nuclear reactions, it's fundamental.
Right, like in stars or power plants.
Exactly. And another key thing is how relativity just explained the behavior of really fast particles, like electrons from radioactive decay, without needing special ad hoc rules. The theory itself gave the right answers.
And it explained that weird experiment, Michelson-Morley.
Ah, yes. They were looking for the ether, this substance they thought light waves travel through. They expected to see differences in light speed depending on Earth's motion through it.
But they found nothing.
Nothing. A null result. Relativity explained it beautifully. There is no ether, no preferred frame. The speed of light is just constant for everyone. Much simpler.
And then Minkowski gave us this picture of four-dimensional space-time.
Right. He showed that space and time are woven together. Think of rotating something in 3D space. The XYZ coordinates change, but the object stays the same. Minkowski showed the Lorentz transformation is like a rotation in this 4D spacetime, preserving the underlying reality while changing how different observers measure space and time intervals.
Okay, deep breath. Now, let's make the jump to general relativity. This goes beyond smooth motion, right? It includes acceleration and gravity.
Exactly. It generalizes the principle of relativity. And Einstein started thinking about gravity differently, not as an instant force, but as a field, like a magnetic field, created by mass.
And the key observation was things fall at the same rate. Feather and bowling ball.
Precisely. The fact that an object's acceleration in gravity doesn't depend on its mass or what it's made of, this equality of inertial mass, resistance to acceleration, and gravitational mass, how strongly gravity pulls it, was the crucial clue.
How did he use that clue?
With another brilliant thought experiment. Imagine you're in a closed box, way out in empty space. If the box accelerates upwards, you feel pushed down, just like gravity.
Right.
Einstein realized you couldn't tell the difference locally between that acceleration and just being stationary in a gravitational field. That's the principle of equivalence.
So acceleration and gravity are kind of the same thing locally?
In a very real sense, yes. Their effects are indistinguishable locally. And this means the equality of inertial and gravitational mass isn't a coincidence. It has to be true. It also means you can't just switch off gravity everywhere by choosing a different viewpoint.
Okay, if gravity and acceleration are linked, what does that predict about, say, light?
Well, if light follows a curved path in an accelerating frame, which it does, then the equivalence principle implies light must also follow a curved path in a gravitational field. It bends around massive objects.
Light bends.
Yes. And this also means the speed of light isn't strictly constant everywhere in general relativity. Its speed can change, depending on the local strength of gravity.
Well, wait. Doesn't that contradict special relativity?
Not really. It includes special relativity as a limiting case, where gravity is negligible, space-time is nearly flat, and the speed of light is effectively constant, just like SRR. General relativity is the broader picture that includes gravity.
Does gravity affect time, too?
It does. Gravitational time dilation. Clocks run slower in stronger gravitational fields. A clock at sea level ticks slightly slower than one on a mountain.
Seriously?
Seriously.
Yeah.
It's a tiny effect in everyday life, but it's real and measurable. And actually, it's crucial for things like GPS. The satellites are in weaker gravity, so their clocks run faster than ours on Earth. We have to correct for that using general relativity, otherwise GPS wouldn't work accurately.
Wow, okay. So space is curved, time is relative. Does regular geometry even work anymore, like pi and circles?
Not in strong gravity or accelerated frames. Think about measuring a spinning carousel. If you try to measure the circumference with rulers laid end to end, those rulers near the edge would actually be length contracted from the perspective of someone not spinning. Your measurement of the circumference divided by the diameter wouldn't quite be pi. Geometry becomes non-Euclidean.
So how do you even do geometry in curved spacetime?
Mathematically, you use a more flexible system called Gaussian coordinates. It doesn't assume flat space. And the specific way distances and times are measured at each point is described by something called the metric tensor. It's like a set of rules telling you how geometry behaves locally, and it changes from place to place depending on the gravity.
And the rules governing how mass creates this curved geometry, those are the field equations.
Einstein's field equations, yes. They are the core mathematical statement of general relativity, linking the curvature of space-time, the geometry, to the distribution of mass and energy within it.
Did this theory actually explain anything the old Newtonian theory couldn't?
Oh, absolutely. Its first big success was explaining a tiny wobble in the orbit of Mercury. Newton's laws couldn't quite account for the full wobble, the advance of its perihelion. General relativity predicted it perfectly, just based on the sun's gravity curving space-time nearby.
That's impressive. And it changed how we think about the whole universe, too. Cosmology.
Big time. Newton's theory had issues with an infinite universe filled uniformly with stuff. General relativity opened the door to describing a universe that could be finite in size, but have no edge or boundary. Think like the surface of a sphere, but in higher dimensions.
A finite but unbounded universe.
Exactly. And it proposed that the overall geometry of the universe is determined by the matter and energy within it. The universe's contents dictate its shape.
And people actually saw that light bending you mentioned.
They did. Famously, during a total solar eclipse in 1919, expeditions measured the positions of stars near the sun. Their light had been deflected as it passed through the sun's gravitational field by exactly the amount Einstein's theory predicted. It was huge news.
Any other predictions?
Well, there's gravitational redshift. Light climbing out of a strong gravitational field loses energy, shifting its color slightly towards the red end of the spectrum. That was harder to confirm definitively early on, but it's another verified prediction now.
So stepping back, as you, our listener, keep thinking about this, it's clear Einstein just completely reshaped our view of reality. Space, time, gravity, they aren't fixed stages, they're dynamic players linked together.
Yeah, and what seems paradoxical, like time slowing down or space bending, actually becomes necessary once you accept those core principles, like the constant speed of light and the equivalence of gravity and acceleration. Our intuition just isn't built for this scale.
It really makes you wonder, doesn't it? What other limitations does our everyday intuition have, and how will future discoveries, maybe exploring things like dark energy or quantum gravity within this framework, continue to stretch our understanding of what reality even is? Something to ponder as you explore these ideas further.